All right, chemistry class, I'm coming to you on a beautiful fall evening here, and we are going to be looking at chapter 7, which is all about chemical formulas and chemical compounds. Now, if you remember in chapter 6, we looked at bonding. Why do elements form these compounds? And we determined that it's because it puts them in a more stable position, a lower energy position. So most of the elements do not have a full outer energy shell, and they accomplish that by combining with other atoms it could be the same element or other elements, and forming compounds in order to be more stable. Well, in this chapter we're going to be looking at the formulas that we use to describe those compounds and the names of those formulas for those different compounds. Okay? All right. In your notes, you're taking notes on this video, remember, the first thing I'd like you to do is to respond to these two questions, and they're kind of review questions to get us thinking about what we've learned and then how that ties into what we're going to learn here. So pause the video, answer these two questions right now in your notes. Those are the first things I should see. Okay, section 7.1, you can put that as a heading, and the title is Chemical Names and Formulas. Okay. All right. Basically, we know that all of the elements on the periodic table are going to combine to form compounds, except for those that are pretty much stable, like the noble gases. They really are not very reactive. And there are other elements, too, that are not very reactive. Gold, for example, silver, some of those precious metals that are fairly stable by themselves and don't form compounds. But in most cases, elements are going to form compounds, as we described. And we get millions and millions of different compounds just from 100 or so elements. That's amazing. That's absolutely amazing. Okay? Basically, the formula that we have devised, that scientists have devised, give us information about what elements are in the compound and how many of each element. Okay? So the formulas are going to tell us what? The number and the kinds of atoms that are in the compound. We want to know which elements, the atoms or which elements are in the compound, and how many of each of those are in the compound. Okay? All right, so for example, if we see a formula like this, here we have the symbols for two elements, carbon, C, and H is hydrogen. That's telling us what's in the compound. And then these subscript numbers are telling us how many of each element. So this is telling us that this molecule has 8 carbon atoms and it has 18 hydrogen atoms. And they're all bonded together. Somehow they're sharing pairs of electrons in order to keep them together in a compound. Okay? Now, in an ionic compound, remember there's a collection or an array, or sometimes called a lattice of positive and negative ions that are bonded together. Okay? And we can write a chemical formula for an ionic compound, and that is going to give us the simplest ratio of positive and negative ions that come together so that the overall compound is neutral and has no charge. Okay? So we're first going to look at ionic compounds. There are two different ways to name compounds. One is if it's ionic. We're going to talk about that first. And two, if it's molecular or covalent. So there's two different naming systems. The formulas are very similar. We still use the element symbol with a subscript to tell us how many of those atoms, or how many of the atoms of that element are in the compound. But the naming is slightly different. So let's start with ionic. Okay? Now this is an ionic compound right here. This is aluminum, and it's bonded with a polyatomic ion. We'll talk about that in a second. But if you see a metal bonded with non-metal, pretty guaranteed that it is ionic compound. Okay? So this is telling us that this has 2 atoms of aluminum, and it's bonded with a group. Here's a group, SO4. That is sulfur and 4 oxygens. That's a whole group, okay? It has 4 oxygens and 1 sulfur. That whole group right there, you have 3 of that group. So it's like aluminum and then another aluminum somehow bonded here. I don't know exactly how they're bonded, but then it's bonded to 3 different SO3 groups. Okay? So you have to imagine you've got 2 aluminum bonded with, it's probably actually more like an aluminum and it's surrounded by the SO3s like this. Okay? And then you've got another aluminum surrounded by SO3s. So somehow you've got positive and negative ions and they're surrounding each other in this ionic compound. Okay? So we have 2 aluminums. I'm just showing you the formula. Just look at the formula right now. I want you to look at a formula and understand what it's telling us. 2 aluminum atoms bonded with 3 groups of this SO4 polyatomic ion. So now let's break this down. How many total atoms of each element are there? There's 2 aluminums, 2 times the aluminums, and there are 3 groups of this SO4. Inside this group there's 1 S, but that's 3 times. So there are 3 sulfurs, and there are 3 times 4, there are 12 oxygens. That's how many total atoms are in one of those compounds. Okay? All right. When we talk about ionic compounds, remember this is a result of electrons being transferred from one, the metal, to the other, the non-metal, and it forms ions that then are attracted to each other because they have opposite charges. And they're going to come together in a ratio so that you have an overall neutral compound. When we talk about ions, it may be an ion of just one type of atom, so that would be called a monatomic. Monatomic means one atom, one type of atom, and it's ionic. It's an ion because it has a charge on it right there, +3. If it's a +3, what does that mean? It has 3 more protons in its nucleus than the number of electrons around its nucleus. Okay? 3 electrons have been stripped away from it by probably a nonmetal. So this has a +3 charge on it, and that monatomic ion. Okay? Here is sodium. It's monatomic, and it is a positive charge on it. Means it has 1 more proton than the total number of electrons because an electron left. Here's a chloride. Notice when it's a nonmetal, the ion ends in IDE. IDE. We'll talk about that later. This is a chloride ion, and it has a negative charge, a -1 charge. Why? It has 1 more electron around its nucleus than the total number of protons in the nucleus. Okay? Now, when you are trying to determine the charges on these ions, it actually is fairly straightforward. I mentioned this before when we talked about valence electrons. Okay? Anything in group 1 has 1 valence electron. Those are metals in group 1 have 1 valence electron, and they like to lose that electron. If they lose that electron, they're going to become a +1 charged ion. So all of these are group 1. Group 1 metals have 1 valence electron, which they like to lose, and therefore they become a +1 ion. So the ion that is normally formed from group 1 metals is a +1 ion, a cation, with a charge of +1. Anything in group 2 is going to have 2 valence electrons, which they like to lose, and therefore is going to have a +2 charge on it. A +2 has lost 2 electrons, so it has now a +2 charge. These are all in group 2, all of these metals here. Group 13, remember we jump over the transition elements? Group 13, here's aluminum, that's a very popular one. It is going to like to lose its 3 valence electrons and become an ion of +3. Okay? Now it doesn't just lose those electrons all by itself. Somebody has to take them. A non-metal is going to take them that wants them. Okay? Now let's jump over to the non-metals. Non-metals like to gain electrons. They like to gain electrons. So here we are in group, I'm going to go to the other end of the periodic table, okay, way at the other end. No, the noble gases are group 18. They don't like to gain or lose electrons at all, so we're not going to bother with them. These are group 17. Group 17, they have 7 valence electrons, which means they only need one more to get a complete outer shell of 8. They like to gain electrons. That's how they're going to complete their outer shell. So if they gain 1 electron, they will now have a stable configuration, and they'll have a complete outer full shell. Well, if they gained an extra electron, their charge is going to be -1. All of these are group 17, and they like to form ions with a -1 charge. Okay? This is group 16. I'm coming from the other side now, okay? Group 16, they have 6 valence electrons, which means they only need 2 more to complete their outer shell. And if they're able to do that, if they're able to get 2 more electrons, usually from a metal, they are going to have a charge of -2. These are all in group 16. So all of these like to gain 2 electrons to complete their outer shell, and therefore they're going to have a -2 charge. These are in group 15. Group 15 is going to have 5 valence electrons. Therefore, they just need 3 more to complete that outer shell to get their octet. So 3 more electrons that they pull from a metal somewhere, and they're going to have a -3 charge on their ions. Okay? So there's group 1, group 2, group 13 are all metals that like to lose electrons. Group 15, 16, and 17 are all nonmetals that like to gain electrons. Well, you may be asking, what about group 14? That would be like carbon. Carbon has 4 valence electrons. Is it going to gain 4 or lose 4? Either way, then it would have a full outer shell. Well, it usually likes to share electrons, so it doesn't form an ion very much. Okay? But all of these you should know. You have to know group 1. They have 1 valence electron, and they form a +1 ion. Group 2 have 2 valence electrons, and they form a +2 ion. Group 13 has 3 valence electrons, they form a +3 ion. Group 15 has 5 valence electrons, they like to gain 3, have a -3 ion. Group 16 has 6 valence electrons, they like to gain 2, to have a -2 ion. Group 17 has 7 valence electrons, they like to gain 1 more, have a -1 charge on their ions. These are set. You have to know these. Obviously, you can just refer to them in your notes, but you should know them, okay? Now, notice that I often have been skipping over the transition elements. That's the D block, or groups 3 through 12. 3 through 12. That's because there's some variation there. Because of the D block and the S block and the P block, sometimes they like to lose 1 electron, maybe 2 electrons, and so there is some variety there. And it means that an element in the transition block, the transition elements, those metals, might have a +1 charge, they might have a +2 charge, so they could have multiple charges. For example, iron. Iron right here, that's a metal. It might lose 2 electrons from the s orbital, or it might lose 3 electrons, maybe from the s orbital and 1 from the d, or 1 from someplace else. It has multiple ions that it can form. Okay? So this is a list of metals, and these are mostly in the transition element group, that could have possibly multiple charges. For example, here's a copper. It could form a +1 ion. It could also form a +2 ion. Okay? Iron, I already mentioned, could have a +2 or a +3. Chromium could have a +2 or +3. Tin could have a +4, or it could have a +2, and you just refer to the table, and I'll show you also how you can determine which one it is by looking at the formula. Okay? Now, let's talk a little bit about how 2 elements can come together, and this is going to be a metal and a nonmetal. We're talking about ionic compounds right now, metal and nonmetal, two elements are going to come together, two binary, bi is two, a binary compound that has elements of two different elements, a metal and a nonmetal. Let's talk about binary compounds and how we are going to name them and how we're going to write the formula. Okay? So let's look at an example here. We want to figure out, well, what if aluminum and oxygen want to form a compound? Okay? Here is your metal. Here is your nonmetal. Guess what? Ionic compound. Okay? Now, I know from the periodic table, I look at the periodic table, aluminum is in group 13. It has 3 valence electrons. So it wants to lose those 3. It wants to lose 3 electrons and become what? Aluminum 3+. That's what it wants to do, to be more stable. Oxygen is in group 16. It has 6 valence electrons. If it just gains 2 more, then it would have 8. So it would like to gain 2 electrons. So how are they going to make an agreement between aluminum and oxygen so that they're both happy? Okay? Oxygen wants to gain 2 electrons and it's going to form a 2 negative ion. Well, they have to come together always so that you have a neutral compound. If I just grabbed 1 aluminum and 1 oxygen, this aluminum has a 3+ charge on it, this oxygen has a 2 negative, that doesn't add up to 0, 1 of each. They have to come together in the correct ratio so that you form a neutral compound, and then everybody is happy. Okay? Let me show you kind of a diagram here of what it would look like using our dot diagram. Aluminum has 3 valence electrons. Okay? I'm just showing the outer 3. Oxygen has 6. Okay? Aluminum wants to give up these 3. So aluminum gives up 1 to this oxygen, and it gives up another 1 to this oxygen, and now the oxygen has 8. But it still has another 1 here that it would like to give up. How's it going to do that? Well, there has to be another oxygen that comes in, also with its 6 valence electrons. So now this aluminum gives its valence electrons, third one, to this oxygen here. Okay? But now this second oxygen is still not happy. It's saying, great, you gave me 1, but I still want another one. So now another aluminum comes into the picture. It has 3 valence electrons. Okay? Well, that's fine and good. Let's see what happens here. This aluminum gives its valence electron there. But now this aluminum has 2 more valence electrons. Says, hey, that's great, but now I have 2 more that I'd like to get rid of. And they call in 1 more oxygen. 1 more oxygen here. And now you'll notice that this aluminum can give its valence electron to that oxygen and its other valence electron to fill that other space for the oxygen. Now everybody's happy. Look at the ratio that they had to have in order for everybody to be happy. 2 aluminum atoms had to give up each of their 3 valence electrons so that the 3 oxygens can fill each of their 2 spaces. Okay? So they have to combine in a 2 to 3 ratio so that everybody is happy, and we now have a neutral compound. We had ions here because this lost 3 electrons, 1, 2, 3, and this one lost 3 electrons, 1, 2, 3. You have an oxygen 2 negative because it gained 2 electrons, but so did this one, and so did this one. Now, if we bring in 2 aluminums and 3 oxygens, you're going to have a neutral compound. Look at the final formula for the compound. It is neutral. No charges are shown on there. Only when they're apart are there charges. Okay? Now I'm going to show you a little trick so that you can always get the correct formula. If you know the charge on these separate ions, then you know what ratio they have to combine in. You basically take the absolute value of the charge from aluminum, and that becomes the subscript for oxygen. You take the absolute value of the charge on oxygen, and that becomes the subscript for aluminum. That is a quick and easy way, you kind of crisscross the numbers to come up with your formula for your ionic compound. Always works. Always works. Okay? Now, how do we name this? The way we name it is the metal retains its name. It's still aluminum. But the nonmetal, because we want to kind of designate it as an ionic compound and have it be known that it is now in a formula with a metal, the ending of the nonmetal is going to change to IDE. So instead of oxygen, it is oxide. Oxide. So this is called aluminum oxide. Aluminum oxide. Now, from this name, I can also come up with a formula. You should be able to, if I give you the name of an ionic compound, come up with a formula. If I give you the formula, you should be able to come up with a name. Okay? In an ionic compound, I do not have to tell you in this name how many of the atoms there are of each, because you figure it out from the charges. Aluminum, I know it forms a 3+ ion. Oxide, I know that's a 2- ion. And so, how many of each? I know there has to be 2 aluminum and 3 oxygen. I know that's the formula of aluminum oxide. Always, 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 always. Because the charge on aluminum is always +3. The charge on oxygen is always -2. Done. Okay? So let's just practice a few here. Potassium and iodine. So potassium is in group 1, it forms a +1 ion. Iodine is in group 17, it forms a -1 ion. Well, that's easy. They're going to come together, one of each, to form a neutral compound. It's just Ki. That's potassium iodine. Magnesium and chlorine. Magnesium is in group 2, it forms a 2+ ion. Chlorine is in group 17, it forms a -1. So this is going to be MgCl2. Notice I'm going to need 2 of these and 1 of those, 1 of the magnesium. This is called magnesium chloride. The ending of the nonmetal changes to IDE. Okay? Let's name a few. Let me do one more. Let's do aluminum and nitrogen. Aluminum forms a +3. Nitrogen is in group 15, forms a -3. Well, you just need 1 of each. I know this is a 3 here. You would think, oh, I'm going to put a 3 for this and a 3 for this, but we always reduce it to the lowest whole number ratio. 3 to 3 is the same as 1 to 1. I just need 1 of each. So this is aluminum nitride. Okay? Let's name these. This is silver, and this is chlorine, but when it's in a formula, it's chloride. Done. Now, when I see silver chloride, I know the formula also, because silver is always, this, you can just look, I'll give you this one. This is not a necessarily one that you should know, but it's an easy one to know. Silver is always a +1. Chloride is a -1. They have to be in a 1-to-1 ratio to make a neutral compound. Okay? This here, this is calcium. The metal stays the same, and Br is bromine, but as a ion in a compound, it's bromide. Calcium forms a +2 ion, bromine forms a -1. So, how are they going to come together? They're always going to come together in a ratio so that you have a neutral compound. Now, I put a 1 there, but we usually don't write the 1. But that's calcium bromide right there. Okay? Now, I mentioned before there are some metals, the transition metals, the transition elements, that could have multiple charges. So what do we do about that? How am I going to know which one it is? Well, that's why when we're going to use a Roman numeral to decide, or to show, I mean, which ion we're using. Are we using iron 2+ or iron 3+? And we're just going to name that iron 2 if we use the 2+, iron 3 if we use the 3+. It's just that simple. Okay? This is called the stock system of naming ionic compounds. Okay, so let's use this one for example. Let's go here. This is Cu. Cu is copper, and the Cl is chlorine. So copper has multiple possible ions. It could be a +1, it could be a +2, maybe a +3. How do I know? Well, if I look at the formula, there's a clue there for me to figure it out. Chlorine is always a -1 ion. Okay? And if it takes 3 of these here to neutralize or to combine with copper to give me a neutral compound, then this copper here must be what? Must be a +3. Remember, you're kind of doing this in reverse here. There's the formula. Where did this subscript come from? Right there. Where did this subscript come from? Right here. Okay? I can kind of give you, if you go in reverse order, I can kind of give you the charge on the original ion. So how do we name this? This should be copper 3 actually. Copper 1, 2, 3. Okay? So copper 3, because chlorine is a -1 and it takes 3 of them. So I would name this copper 3 chloride, ending IDE for the nonmetal. Okay? IDE. Now, let's look at this one here really quick. We'll do a couple practice. This is lead 2+, and lead can have multiple ions. So we have to make sure that if it has multiple ones, that we use a Roman numeral. If it doesn't have multiple ones, if it's always a +1, always a +2, you don't have to use a Roman numeral. There are no other options. But lead has multiple ion possibilities. So this is lead 2 chloride. And what would be the formula? It would have to be, this +2 is going to give me the subscript for chlorine. That's my second part. And this -1 is going to give me the subscript for lead, which I'm not going to write the 1. So this is lead chloride. Lead 2 chloride. Okay, lead 2 chloride. How about iron 3 and oxygen? So this is iron 3 oxide. And the formula would be, let's just write the symbols. And then I take this 3 and it becomes a subscript for the oxygen. This 2 becomes a subscript for iron, and you're done. There's iron 3 oxide. Notice this iron 3 right here doesn't tell me how many atoms of iron are in the compound. It tells me the original charge on that iron ion. Okay? All right, what if I just gave you the formula here? Well, copper has multiple ion charges, but I know oxygen is always a 2 negative. And notice 1 copper to 1 oxygen. So this must be a copper 2+, 1 to 1. So this is copper 2 oxide. I have to put the 2 there because copper has multiple ion possibilities. Okay? Now, here are, I mentioned some polyatomic ions. You don't have to memorize this. You can refer to this chart. Basically, these are groups of nonmetals usually that are bonded together covalently, but they have a charge on them. So this is a group of nonmetals that have a charge on them. This is a group of nonmetals that have a charge on them. This is a group of nonmetals, a carbon and 3 oxygens bonded together, but overall has a charge because that group has 2 more electrons than the total number of protons in that group. So these are many atoms, polyatomic ions. And these can also combine with metals to give you ionic compounds. Okay? That you just treat it like you would with a monatomic ion. Just look at the charge, and that's going to tell you how many of these groups, how many of this group needs to combine with a metal to give you a neutral compound. Okay? So let's look at some of these. All right? So let me just show you. Let's just do some of these right here. Okay? Lithium nitrate. Do you see the ending here? If you see ATE, ITE, it usually is a polyatomic ion. Okay? IDE means a monatomic ion. IDE ending means it is a non-metal ion. But if it's 8, let's just look at these names up here for a second. Look at these names. This ends in 8, 8, ite. Okay, there's an IDE, there's an exception. Okay, 8, 8, 8, 8. There's an I, there's an exception. There are some exceptions. But a lot of times these polyatomic ions end in ite or 8. Okay? Now there are some others that end in, these are negatively charged ions and some are positively charged. But there are some exceptions here, but you just have to become familiar with them. Here's hydroxide. That's a popular one. But again, 8 and ite is often a polyatomic ion. Some of the differences that the exceptions that you should know ammonium is a polyatomic ion. You should know that hydroxide is a polyatomic ion. Those are some that don't end in ite or 8 that are very, very common. Okay? So back to naming these with polyatomic ions. Here I have lithium, there's my metal, and nitrate. There's that 8, it's a polyatomic ion. Lithium forms a +1 ion. How do I know that? It's in group 1. Nitrate, okay, I'll just refer to the table up here. Nitrate, there's my nitrate. NO3, and there's the charge, -1. Okay? NO3, -1. So this has a +1, this has a -1. They have to come together in a 1-to-1 ratio to get a neutral compound. So this is going to form what? Lithium nitrate NO3, just like that. One of the lithium, one of the nitrate, and you're done. Okay? Let's look at this one. Calcium nitrite. Calcium nitrate. Calcium is a +2 ion because it's in group 2. Nitrite, ITE ending. Oh, there it is. Let's see. Right up here. Nitrite, there it is. And I don't know why that 4 is there. It doesn't need to be there. Nitrite, NO2 negative. So NO2 with a negative charge. NO2 negative. How are they going to come together so that you have a neutral compound? Well, same thing. I'm going to write it up here, calcium and nitrite. I need 2 of the nitrite. I need 1 of the calcium. I'm going to put a 1 there. I normally don't write it. And I need 2 of these. So I need 2 of this whole group. I'm going to put that in parentheses and put a 2 outside of that. Here is the 2 that's telling me I need 2 of these nitrates, 2 of these negatives, to neutralize the 1 plus 2. Okay? So that's how you write it. When it's a polyatomic ion and you have multiple ones of them, you got to put in parentheses like this and put the number outside. That is calcium nitrite. Okay? Let's do one more. Let's do sodium. Sodium is in group 1. It would form a +1 ion. Carbonate. Oh, there's a polyatomic ion. Let's look up here. 8. Carbonate. There it is. Carbonate. CO3 with a charge of 2 negative. CO3 with a charge of 2 negative. CO3, 2 negative charge. How many of each have to come together to give me a neutral compound? This is a +1, so I'm just going to have 1 of the carbonate. And this is a 2 negative, so that's going to give me 2 of the sodium ions. Now I've got a neutral compound. Okay? All right. These naming should be easy. This is calcium metal. Just look on the periodic table. And OH, oh, there's a group. That group is a polyatomic ion. Where is it? It is right here. That is a hydroxide. And it's just named just the way it appears on the polyatomic ion table, hydroxide. And you're done. That's how you name it. It's just that easy. Here's a metal. That's potassium. And then I see, oh, the rest of them are nonmetals in a group. ClO3. What is that? Let's check. ClO3. ClO3 is right here. Chlorate. ClO3. So I just name it using the name of that polyatomic ion. Chlorate, and I'm done. Okay? This is, you have to be careful here. See this group? You have to recognize that one. And here's a group here. This first group is ammonium. I told you have to be able to recognize that guy. And the second group, you have to recognize him. That is hydroxide. So that is ammonium hydroxide. Okay? Here's iron and a group. This is iron I think Cr4 is chromate. There it is. Just name it just like that. So that is iron, and this actually is going to be iron 3. As you see, you need 3 of those. Oh, let me just double check there. Chromate is a +2. Yep, I think that's right. So this is iron. I have to put 3 because iron can be multiple charges. Iron 3 chromate. Okay? All right, that's some good practice there. All right, now we're going to talk about no longer ionic compounds. We are going to talk about covalent or molecular. Remember, this is where they are sharing electrons now. Before, I was talking about where there's a transfer of electrons, ions are formed, and they form an ionic compound. There is a specific way to name ionic compounds. That's what I just finished talking about. Now we're going to talk about covalent or molecular compounds, and the naming process is slightly different. We are going to use prefixes to tell us how many of each atom are in the molecule. So here are the prefixes that we're going to use. Hopefully these are somewhat familiar to you. If there's one atom of a particular element, we're going to say mono. 2 is di, 3 is tri, 4 is tetra, 5 penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, and deca for 10. Okay? Remember, these are only for covalently bonded compounds. A nonmetal with another nonmetal. We don't use prefixes for ionic compounds when we have a metal with a nonmetal, because we don't need prefixes because the way they combine is already set. Okay? All right. So, if you have phosphorus and you have 4 of them combined with oxygen, 10 of those, the formula is written in a very similar fashion as before, but the naming is different. Because nonmetals can combine in different ratios, they can share electrons differently, we have to use prefixes. They don't always come together in a set fashion, a set ratio. So phosphorus and oxygen could come together in a 4:10 ratio or some other ratio. So we have to write down the prefixes. So this is going to be phosphorus. There's 4 of them, so it's tetra phosphorus. There's your 4 prefix, and the name of the first nonmetal stays exactly as it is on the periodic table. And then 10 is deca, and the second nonmetal is also going to end change its ending to IDE. So this is decoxide. Now I know the prefix is deca, but you're never going to see 2 vowels next to each other. If the prefix ends in a vowel and your element ends in a vowel, you're going to drop the vowel of the prefix. So it's decoxide. Okay? There's your 4 for the first nonmetal. There's the 10 for the second nonmetal. The second nonmetal's ending changes to IDE. Okay? So what is this going to be? It's really simple. Prefixes, covalently bonded compounds are easy to name because you just use the prefixes. So this is sulfur. Or you don't need the mono if it's the first one. If there's just one sulfur and it's the first element in the compound, you don't need to write monosulfur. It's just sulfur and then 3 trioxide. Okay? Tri. Now I just said if there's a vowel ends in the prefix and your vowel starts the name of the second nonmetal, you drop it, but actually this you don't. Okay, it's trioxide. Okay, only you drop it, I think, if it's an A or an O. If it ends in O or A and the nonmetal for that element also starts with a vowel, I think that's when you drop the O or the A. Okay, but not the I or the I in tri or the I in bi. So this is iodine, tri, chloride. Notice the ending, chloride, okay? This is phosphorus, phosphorus, pentabromide, pentabromide, okay? And if you got the name, the formula is easy. Carbon, tetraiodide. Oh, and there you can see there's two vowels together. So if it starts with an I and you have the prefix ending in an A, you don't drop it. Only if it ends in an A and it begins with an O, I guess. It gets a little confusing, but you'll get used to it. Tetraiodide. Tetraiodide is going to be 4 iodine atoms, and it just looks like that. Carbon, tetraiodide. Phosphorus, trichloride. Done. Dinitrogen. Okay? 2 is di. I might have said bi before. It's di. Okay? Dinitrogen. There's 2 of them. Trioxide. Done. See how easy that is? That's really easy. Okay? Okay. So, naming molecules should be easy. I should be able to give you the formula. You should be able to give me the name. I give you the name. You should be able to give me the formula. Okay? It's just that easy. Silicon, Si, dioxide, O2. Okay? Trisilicon, 3 silicon atoms. Tetranitride, 4 nitrogen atoms. Done. Okay? Now, I am not going to be asking you about naming acids and oxyacids, so you don't need to worry about this section right here. Okay? Don't have to worry about that. We're going to be using acids and bases later on in another chapter, and you're going to become familiar with a lot of the names of acids and bases just by using it. So we won't worry about it right now. Okay? All right, so that's section 7.1. And when we get into 7.2, we're going to talk about something called oxidation numbers. Okay, I changed my mind. We are not going to do section 7.2. We're not going to talk about oxidation numbers. We're actually going to save oxidation numbers when we do another chapter and we talk about electrochemistry, because it relates very well to electrochemistry, and so we're going to save it until then. So don't worry about 7.2 right now. Oxidation numbers will come up later. Okay? Okay, let's talk a little bit more about chemical formulas and what we should be able to do with a chemical formula. Some calculations that we should be able to do. Okay? We should be able to find a few things. The formula mass, the molar mass, and the percent composition, and that's by mass. These are the 3 things that we're going to talk about right now, and you should be able to find those 3 things by looking at the formula of a compound. Okay? Alright, let's first talk about the formula mass. The formula mass is the sum of all the average atomic masses of the compound's elements. It's really easy, actually. Okay, all we're going to do is simply this. Let's just take water. All you do is look on the periodic table. All of the masses are right on the periodic table. So all I do for water is I realize in the formula there are 2 hydrogens. 2 hydrogens right there. And there's 1 oxygen. 1 oxygen right there. And when that's the case, all I do is I look on the periodic table, and I know that each oxygen has an atomic mass of 1. Okay, 1. 1, that U is there is an AMU, atomic mass unit. 1 AMU. So that's 2 times 1, or it's 1.01, so it's 2.02. Each oxygen has an atomic mass of 16 AMU. So 1 times 16 is 16. 16 plus 2.02, I get 18.02. That is the average atomic, or I should say molecular, or formula formula or molecular mass for water. Okay? Just add them together, taking into account how many of each you have. The molar mass is simply numerically equal to the formula mass, but it's going to be in grams. It's in grams. Okay? It's going to be in grams because the molar mass is in grams, not in AMUs. So let's do the same thing for water. Here's all you do. Same formula, 2 hydrogens. That means not just 2 atoms now. We're saying this 2 is representing 2 moles. Remember, each mole is 6.022 times 10 to the 23rd. It's a huge number. But that's the quantity we use in chemistry, kind of like 12 is a dozen. That's the number that we use. This is a mole. So when I have this many hydrogen atoms, that's a mole. And if my formula says H2, I'm going to say there are 2 moles of hydrogen. Not just 2 atoms, but now 2 moles of atoms. Well, 2 times 1.01, just like we did before. But look at the unit. The unit is no longer AMU, it's grams. That number on the periodic table, that mass on the periodic table, if the unit is AMU, that's the mass of 1 atom of that element. If the mass is grams, that's the mass of a mole of that atom. Okay? Same number, different units. So I take my 2 moles times 1.01 grams. I have 2.02 grams of hydrogen atoms if I've got 2 moles. 1 mole of oxygen has a mass of 16 grams. 16 grams of oxygen, 2.02 grams of hydrogen. Together is 18.02 grams for what? A mole of water. A mole of water has 2 moles of hydrogen and 1 mole of oxygen. But this is a mole of water. Okay? All right. Let's look at this guy right here. This says find the formula mass, meaning the individual atoms, the mass of the individual atoms added up together. Okay? So I'm not gonna come up with the numbers. I'm just gonna walk you through this. You'd have to look at the periodic table. But all you do is you look at this and say, okay, there's 1 calcium atom, and I would then multiply 1 times the atomic mass of calcium. I get it straight from the periodic table. 1 times this number, and I write that down. How many nitrogens are there? Well, in the group, in this nitrate group, there's 1, but there are 2 of the group. So 2 times 1, 2 nitrogens, and I would multiply by the atomic mass of nitrogen from the periodic table and write that down. How many oxygens are there? There's 3 in the group, but there's 2 groups. So 2 times 3, there are 6 oxygens. Times oxygen's atomic mass, I write that down, and I add up these 3 numbers to get the total mass, of the formula mass of calcium nitrate. Okay? How many moles of atoms are there in each compound? Well, assuming that this is 1 mole, I have a mole of this, I have 2 moles of aluminum, 3 moles of sulfur. Just like if I was going to say I have 1 compound, then I have 2 atoms of aluminum and 3 atoms of sulfur. Okay? Here I have 1 sodium, 1 nitrogen, 3 oxygen in a single compound. Or if I'm talking moles, let's talk about moles on this one. If I have a mole of this compound, I've got 1 mole of barium, I've got 2 moles of oxygen, and 2 moles of hydrogen. Okay? What if I want to find the molar mass? Well, I look at my formula. I've got 2 aluminum, 3 sulfur. I look on the periodic table, just find the same mass number on the periodic table, but now it's in grams because we're talking moles. So I find the mass of aluminum. I take 2 times that mass, write it down. I take 3 times the molar mass of sulfur, and I write it down, and I add those 2 numbers to get my total, what? Mass of 1 mole. That is called the molar mass of that particular compound. Remember before we did conversions from mass to moles to number of particles. Molar mass is what we need to convert from mass to moles or moles back to mass. We have to go across the molar mass bridge to get from one to the other. You have to, okay? If I want to go from mass and I want to find out moles, I would, if I'm going this direction, I divide by the molar mass. If I know the mass, I would divide by the molar mass to find out how many moles I have. And then if I want to find out, okay, how many particles is that, or how many molecules, let's say, I multiply by what? Avogadro's number, 6.022 times 10 to the 23rd. If I'm going the other direction, if I know how many molecules I have, I divide by 6.022 times 10 to the 23rd. That gives me the number of moles, and then I would multiply by the mass of 1 mole to find out the total mass of all my moles. Okay? It's the same thing that we did when we had just an element. It's the same process. This is saying you're doing the same thing for a compound as we did for an element in a previous chapter. Exactly the same thing. Okay? Let's walk through this example together. What is the mass in grams of 2.5 moles of oxygen gas? Now, oxygen gas is diatomic. It always appears as O2 in nature. Okay? So 2.5 moles of O2. So what you do is, we're going to start with this many moles. Okay? We have this many moles of O2. What I'm going to do is, if I want to go from moles to mass, I'm going to multiply by the molar mass. Now this is O2. That's 2 oxygens. Each oxygen has a molar mass of 16. So that's 32 grams per mole. I don't just have 1 mole, I get 2.5. So I take 2.5 times 32 to get my 80 grams of oxygen gas. 2.5 moles of oxygen have a mass of 80 grams. 1 mole of oxygen has a mass of 32. Okay? It's O2, remember, O2. Alright. This is breaking it down. This is a good practice for you here. How many moles are in 4.5 kilograms of calcium hydroxide? Well, notice it says kilograms here, so that is 4,500 grams. Kilogram is 1,000 grams, so that's 4,500 grams. So what is the mass of calcium in 1 mole? Well, again, you look on the periodic table, you would find mass in 1 mole. Okay, that's 1 mole here. So we'd find that number on the periodic table. Oxygen, we have actually 2 moles of oxygen. See this oxygen here? But it's double that. So it says, what is the mass of oxygen in, I'm going to put here 2 moles. Oh, sorry. What is the mass of oxygen in 1 mole of calcium hydroxide? But we have 2 moles of oxygen. Okay? So it would be 2 times the number from the periodic table. And hydrogen, we have 2 moles of hydrogen in this compound as well. See the 2 outside the OH there? So I'd make 2 times the mass of hydrogen from the periodic table. I take all of these numbers and I add them to get the molar mass of calcium hydroxide for a mole. This is per mole. Then, if I've got 25 this should be 4.5. I think we have 4.5. I don't know what says 25 there. 4.5 grams of this calcium hydroxide. I know there are 1,000 grams per kilogram. That's what I just said before, 4,500. And then I would have to divide by this molar mass here. Okay? So whatever this number is, I'm dropping it in there. I'm dividing 4,500 by that molar mass to find out how many moles I have. Okay? All right, you can look, I would encourage you to look through this example. Very, very good. You can pause the video here and walk through it as I scroll down, or you can pull open the PDF file of this from the assignment. Okay? All right, let's look at percent composition now. Okay? Okay, to find percent composition, what we're finding is we're finding the percentage by mass of each element in the compound. Okay, so since we already found the molar mass or the formula mass, all we're doing is we're taking that and we're finding out how much each element, the mass of each element is by percentage of the total mass. Okay, let's look at an example here. All you're going to do is you're going to take the mass of each element in the sample, divide by the total mass, multiply by 100 in order to get your percent. Okay? Here is an example. Let's take this formula right here. This is copper 1 sulfide, and we're going to find out what percent composition is. We're going to find the percent composition of copper and percent composition of sulfur, each element in the compound. So the first thing we have to do is we have to find the total mass, which we did previously. So we already did that. In our compound, it is copper Cu2 sulfide. There are 2 coppers for every 1 sulfur. So if we're talking moles, in 1 mole of this compound, there are going to be 2 moles of copper for every 1 mole of sulfur. Okay, so 2 moles of copper, if you look on the periodic table, the molar mass for copper is 63.55 grams. So if you have 2 of them, that's 127.1, just double it. 1 mole of sulfur, if you look on the periodic table, the molar mass of sulfur is 32.07 grams. So we get 1 of those, just 32.7. You add those together, and this is the total molar mass for this copper 1 sulfide. Now we want to find out what percentage of this total mass is copper and what percent of the total mass is sulfur. So all you do is you take the individual masses of each element, in this case copper, and divide by the total and multiply by 100. So 79.85% of the total mass is because of the copper in the element. Do it for sulfur, take the 32.07, divide by the total, multiply by 100, 20.15% of all of the mass is due to the sulfur. Okay? These two percentages should add up to 100, right? I know we're going to round off, so maybe it's not exactly 100, but they should be pretty close to 100%. Okay? So, we'll do the numbers here. I'll just walk you through the procedure if we want to find the percent composition. And when it says percent composition, it means of each element in the compound. So to find the molar mass of lead, I have 1 mole of lead in a mole of this compound. So I would multiply that by the molar mass of lead. Okay, and I would get that number. Then I have 2 moles of chlorine, so I'd multiply that by the molar mass of chlorine, and I get a number, and I add them together in order to get the total. This would be the total molar mass of copper, it's lead 2 chloride. Okay? Now I figure out, okay, what percent of that total is due to the lead. So I take the mass of the lead, which was this number, and I divide it by the total, which is this number right there, multiplied by 100, and I have my percent composition of the lead. I take the mass of the chlorine, which was this number, and I divide by the total of the whole compound, multiplied by 100, and this would be the percent for the chlorine. Okay? Now one little note here, if we have 3 elements in here, notice that this is, in a mole of this compound, you have a mole of barium, you have 2 moles of nitrogen, and you have 2 times 3, 6 moles of oxygen. So just be aware of that when you're doing the calculations. Okay? I would encourage you to walk through this sample problem right here, read it carefully, okay? You can open up the PDF file and then see if you can find that answer and see if it makes sense for you, okay? Likewise here are some examples for you, and they kind of show you the steps so you can practice those, but there are going to be some practice problems in the review questions as well, okay? Okay, 7.3. In your notes, put down 7.3, determining chemical formulas, and let's write down a few notes here. We've talked about formulas already, and all we're going to do is we're going to talk about something called the empirical formula. And all that is, it consists of the symbols for the elements combined in a compound with subscripts. And we've already talked about that, like H2O, okay? But empirical is going to show the smallest whole number ratio of the different elements, okay? So like if I said H2O, that's the simplest whole number ratio. It's a 2 to 1 ratio. If I said in a compound, in a group of atoms of hydrogen and oxygen, there are 8 hydrogens for every 4 oxygens. Well, that's still a 2 to 1 ratio. So this may be a formula, but this would be the empirical formula. Empirical means it's always the smallest whole number, okay? Smallest whole number. Empirical formulas show the whole number ratio of elements in a compound. Whole number ratio and the simplest. All right? Now, when we do an empirical formula, there's a couple steps. You often will not be given the mass of your sample. So the trick in finding the empirical formula is to assume that you have 100 grams. 100 makes it really easy, and we can use that to find out what the formula is going to be. Okay? Then we're going to convert each mass into the number of moles, and then we're going to divide in order to get that whole number ratio. I'll show you exactly what I mean here. So let's look. Here's a problem where we are told that we have a compound and it has sodium in it, sulfur, and oxygen. We don't know the formula, but we are given the percentages here. So remember before how we were given the formula and we came up with the percentages? Now we have the percentages and we're going to go back to the formula. We're just going to go in reverse. We're going to find the formula for this particular compound. Here's the trick. If you are asked to find a formula from percentages, the first thing you do is you are going to assume that you have a sample that is 100 grams total. The whole sample is 100 grams. Okay? Why 100? Because it makes it really easy when you're doing percentages and you have 100. So if we have 100 grams and 32.38% of it is sodium, that means the mass of the sodium has to be 32.38. 32.38% of 100 is 32.38 grams. 22.6% of 100 is 22.65 grams. And 44.99% of 100 is 44.99 grams. So now we have masses for our 3 different elements. From masses, we can come up with how many moles we have. All you do is you divide by the molar mass for each element. So I'm going to take the mass of sodium and divide by the molar mass of sodium. Where do I get this 22.99? Straight from the periodic table. Okay? This is the mass in my sample. This is the mass of 1 mole of sodium. So I take the mass of my sample, divide by the mass of a mole. This is how many moles of sodium I have in my sample. Do the same thing for sulfur. Dividing by its molar mass, this is how many moles of sulfur we have. Do the same thing for oxygen, dividing by the molar mass of oxygen, and this is the number of moles of oxygen. Now, this cannot be the numbers that go into my formula. I can't say Na 1.408 and S 0.7063 O 2.812. That can't be a formula because you can't have a fraction of an atom. You can't have 1.408 atoms in your molecule of sodium. So we have to find whole number ratio. This is the ratio. This is the correct ratio. but we have to have whole numbers. So what we do is we take the smallest of these numbers, which is 0.763, and divide them all by that smallest number. Notice, all of the mole amounts are divided by the smallest of the 3 mole amounts. And we get close to whole numbers. This ratio, or this division, is 1.99. That's pretty close to 2. Here, obviously this is 1, and divide here, and that's pretty close to 4. So it's a 2 to 1 to 4 ratio, and there is your formula. It is Na2S1O4. That's your formula. Okay? Same thing here. You're given percentages. Assume you have 100 grams. So if you have 100 grams of iron, 100 grams sample, and iron is 63.52, 63.52 grams. And this would be 36.48 grams. Okay? Then you're going to take each of these numbers, 63.52 grams of iron, and you're going to divide by the molar mass of iron. So find the molar mass of iron on the periodic table, take 63.52, divide by that, and you'll have a certain number of moles. Do the same thing for sulfur. 36.48, divide by its molar mass, and you have the moles of iron. Now, if these are not whole numbers, then you're going to divide both of them by the smallest of those two, and that should get you close to whole numbers, and then you'd have the formula F, E, and S, and then you'd be able to fill in those whole number ratios there. Okay? All right. Molecular formulas. We've already talked about molecular formulas. It gives the type, again, the types and numbers of the atoms in the compound. We already talked about that. Okay? Now, this is ethylene, okay? And the formula of ethylene is C2H4. This is the molecular formula, but if I reduce that to whole numbers, the smallest whole numbers, the empirical formula is it's a 1 to 2 ratio, so CH2, okay? This is how the molecule looks. It's carbon bonded to carbon and then bonded to 4 hydrogens. This is the actual molecule. That's what it looks like. But with empirical formula, we're interested in the smallest whole number ratio. It is a 2 to 4 ratio, which really, when you simplify it, is a 1 to 2 ratio. Okay, a 1 to 2. So that's the difference between the actual molecular formula is showing you actually how many are in the molecule. The empirical formula is reducing it down to the simplest whole number ratio. Okay. All right. That basically is what we need to cover for 7.4 there, okay? And that pretty much concludes the chapter 7. Now what I'm going to do is I'm going to make another video that walks through and continues to walk through some of these calculations, because that can be the hardest thing. In fact, what I think I'll do is I'll try to make another video for these review questions, especially down here where we do some of these calculations, because I want you to really understand the calculations there, okay? So that concludes chapter 7. When we get together, we'll review this, and you'll be able to ask questions, and always contact me if you need help, ladies and gentlemen. Keep working hard.